All right, welcome to lecture 17, or what would have been lecture 17 that would have occurred on March 23rd. Hopefully you're not too far off of that when you're listening to this. All right, so to fully replicate the classroom experience, I would have been playing Heat of the Moment by Asia back from 1982 at the beginning of this lecture, so cue it up if you want to get the full experience. All right, so we're starting a new chapter today, chapter 5, which is thermochemistry, which in most books has a catchy subtitle, something like The Fire Within. All right, the learning objectives. Now this is for this one little mini lecture. I've got 3 videos for today. For this one, you're going to understand the first law of thermodynamics. You're going to recognize various forms of energy present in chemical systems, and you're going to recognize the units of energy. All right, so let's talk about energy. Usually I would probably ask you to shout out some kind of energies that you know. And some of the answers that we usually get are something like radiant energy if it happens to be sunny. Mechanical energy if, I don't know, people like the word mechanical. Chemical energy because, well, it's a chemistry class. If you skipped breakfast, you're probably thinking of energy from food. And if this is too loud or I'm booming my voice, you might think of sound energy. And if it happens to be warm that day, or not, you might think of thermal energy. Now, the very important thing to realize about all of these types of energies, and I'm sure there are more, is that these are all the same. A fundamental part of this lesson is going to be recognizing that energy isn't created or destroyed. It is merely converted from one type to another, although in a later chapter, we will find that not always the way you might like. All right, so let's talk about how this energy conversion might happen. So consider the source of almost all of our energy locally in our little corner of the universe, directly or indirectly. This would be the sun. Now the sun shines down and can help plants grow. So plants are actually still among the most effective solar collectors that we have, and they can convert the sunlight to break carbon dioxide and oxygen to create sugar and grow. And you could have things like corn and bell peppers and chilies. And people could eat that and use the energy gained from those to, let's say, ride a bike. So we're converting the solar energy to food energy that's stored in the chilies and the corn, and then that's converted to mechanical energy by our bicyclist here. An alternative option, the pepper, the corn, and the chilies don't get picked. They just sort of fall down in the field and rot, and or they could be eaten by a dinosaur. Let's say I forgot about that, and then the dinosaur dies and rots, and that dinosaur could end up as oil. And at this point, you could do 2 things with that. Number one, you could use that to you could put that in the tank of a bus that has an internal combustion in it, and you could turn that to heat in the engine, which in turn turns into mechanical energy and makes the bus go. Or you could simply burn that oil and heat your house with it. So we have taken what is ostensibly energy from nuclear reactions in the sun. It gets converted to light, radiant energy, and it can be harnessed by things in various ways. The energy from the sun is then stored in this food, which could either be directly turned into mechanical energy or turned into potential energy with the oil here and then turned back into mechanical energy or thermal energy. I think that got most of them, except for sound. All right, so this is ways that energy from the sun is converted into various things. All right, so let's talk a little bit more about this conservation of energy. So the way that it's usually stated, or what we said before, is that energy cannot be created or destroyed. The way that a lot of physics books especially will state it is something pretty grand. The energy of the universe is constant. And this is a big enough deal that we actually call it a law. And specifically, this is one of the more common ways of stating the first law of thermodynamics. Unless, of course, you happen to catch Wikipedia at just the right time, in which case the first law of thermodynamics is simply that you do not talk about thermodynamics. And then usually about a minute later, someone changes it back. All right. Now, the problem is that the energy of the universe, dealing with that is kind of hard because the universe is, quite frankly, a fairly big place. So in the face of that daunting task, scientists do what we usually do, is just make something up. So we have conveniently broken up the entire universe into two parts, namely systems and surroundings. And their definition is actually pretty simple. The system is basically the part of the universe, however large or small, that you would care about. And the surroundings is pretty much the rest of it. Now, that clever definition allows us basically to talk about, instead of having to observe the entire universe, we can actually get by with just observing, a beaker, or if you will, a beaker. Okay. Now, another way of stating this, another way of stating the fact that the energy of the universe is constant with this little breakup is we can now say that any energy transferred from a system has to be, any energy that's left from a system has to go to the surroundings, or the other way around. And it turns out that it is a lot easier to monitor the transfer of energy across your system and surroundings boundary, which makes this a much more palatable way to go. And to be specific here, we are talking about closed systems. So these are a system where matter can't come in or out, neither does energy. So the entire universe constitutes a closed system. And in some cases, you can actually make it much, much smaller. A very good cooler that doesn't leak, for example, could be classified as its own little universe, basically because matter doesn't come in or out as long as it's not leaking. And if it's a halfway decent cooler, energy in the form of heat comes in and out at a very, very slow pace. Now, let's talk about classifications of energy, because scientists, if nothing else, like to classify things. Now, energy, if you are inclined to break energy down into two parts, you would probably come up with this. Kinetic energy would be one of them. And this is energy that is associated with things that are moving. Generally, if you want to put this in equation form, you would say something like Ke equals 1/2 mv squared. Potential energy would be the other one, and this is the energy that depends on the position of an object, usually in a field or relative to other objects. So to give you a couple of examples of this, the potential energy that something has on Earth by virtue of how far away it is from the center of the Earth, gravitational potential, and that is given by the formula mgh, where this is the mass of the object, g is the acceleration due to gravity, and h is the height. Another common one is electrostatic potential. This is the potential energy formed by two objects that have charges on them. And in equation form, it is the product of the first charge, the second charge, divided by r, which is the distance between them. And this big Q here is just a fundamental constant. Now, chemists, wanting to be a little bit different, acknowledge that there's kinetic energy and potential energy, but they give them different names. And before I go about that, remember that it's very important to know that we can freely interconvert between these two kinds, as we stated before. All right, so what do chemists call these things? Well, there's something that we often loosely call chemical energy. And this is potential energy that is stored and released in the arrangement of the bonds. So some arrangements of a particular set of atoms are more energetically feasible than others. And so when chemical reactions occur, you're rearranging, you're breaking bonds and you're making bonds. And depending on how more stable the final arrangement is, energy might be given off, or you might have to put energy in to do that. The other kind of energy, and that's a form of potential energy. The other kind of energy that we talk about a lot is thermal energy, and this is heat, and this is a form of kinetic energy because it is a function of the microscopic motion of the atoms or molecules in the thing. All right, so let's go back to the first law here. So another way of stating the first law is that throughout any particular process, if it's in a closed system, so whether it's part of the universe or whether it's in your good cooler, that energy is conserved during the process. Now, what's this word process that I threw in there? In English, you probably know what it is. In physics or chemistry, it's simply a process is defined as a sequence of events that takes our system from an initial state to a final state. And usually, very often, that is just a reaction. So you've got products and reactants. Now we have this thing called total kinetic energy, which chemists or physicists often call U. You will also sometimes see it called E because, energy. And it is the sum of kinetic energy and potential energy. Basically, all the energies that we talked about beforehand can be either broken up as a form of kinetic energy or potential energy, or in some cases, a sum of both. And the actual phrase that we use for this is internal energy. And again, that's shown with either a U, like I've got it here, or sometimes an E, like I have in this picture here. So this sort of represents the ways that energy is manifested in a chemical system here being a bunch of atoms or molecules, which are a group of atoms. So the ones that sort of end up being kinetic energy are these right here. So atoms can move. They can move back and forth, especially if they're gas molecules, or even if they're liquids or solids, they can move a little bit. If they're gases, they can also rotate, and they can also vibrate. We haven't really told you this yet, but the bonds are kind of springs. Now, there's also the motion of the electrons in the atom. That's really complicated, and we usually don't talk about it too much because it's kind of a small contribution relative to these guys. Now, on the potential energy side, there is a potential energy associated with how the various nuclei and electrons are arranged. So these are charged particles. They exert forces on each other. There's a potential energy associated with their positions. Some positions are better than others, which is why molecules have the shape that they do. All right. So the actual internal energy of a molecule or a mole of molecules is actually a ridiculously huge number because of the energy associated with the nuclear attractions, keeping the nuclei together, which we normally don't talk about in chemistry because those don't change. Now, and beyond huge, and the other thing is that they can't really be directly measured. They can be calculated with some effort. All right. Now, this actually is not a problem because really we don't actually care about the absolute energy of something. What we care about is the change in energy for a process. Again, usually a chemical reaction. And this is really simple. The change in internal energy, delta U, is simply the internal energy of the final state. Let's say it's usually going to be the reactants, or the products, I'm sorry, minus the internal energy of the initial state, which is usually the reactants. All right, now again, this delta thing, I think we've seen it maybe a few times already before. In science, delta always means a change, and it's always the value in the final state minus the value in the initial state. All right, and again, what are the states? Typically, the final state will be just the products by themselves, and the initial state is usually just the reactants by themselves. Now, the last thing I wanted to talk about here is the units of energy. So they are a joule. All right. And so this is a joule, namely a James joule. All right, and it is defined as a kilogram per meter squared per second squared. The other type of energy that we talk about, you see come across here as a calorie. That is an older English unit, and it is equal to 4.185 joules, which is the SI unit of energy. And there's actually a third one, which is another calorie. You'll note the difference here. There is a capital C, and then it's equal to 1,000 little c calories. So this is what's referred to as a nutritional or food calorie. This is because I guess people were uncomfortable with eating a 233,000 calorie Snickers bar, and in this case it's only 233 calories with a capital C. These are also called kcals, kilocalories. All right, so that's it for the first video, and so take a look at this, and there are just 2 more to go.